Hello, my name is Sean O'Hare and welcome to a video where we are going to be helping Janique's Bakery maximize her profits by using calculus. The first step is to understand how the problem is set up. Each regular chocolate cake requires 0.1 pounds of European chocolate, while the extra special chocolate cake requires 0.2 pounds. Currently, there are only 233 pounds of chocolate available at the bakery. The profit function of the bakery is given here, where x is equal to the number of regular chocolate cakes and y is equal to the number of extra special chocolate cakes that the bakery can produce each month. The way we go about solving this problem is by using optimization. This process is used to find the maximum amount of cakes that she can bake with the given 233 pounds of chocolate that she has available. On the next slide, we will show the graph of the original profit function. This is the graph of P of xy. The maximum value is shown here. When we compute and observe the partial derivatives on the next slide, this will make sense since this is the point that is the only critical point on the curve. Once we compute the partial derivatives of P of x and P of y, which are shown here, this being P of x and this being P of y, we can then graph them against each other. This is shown on the next slide. Here we have the graphs of P of x and P of y. The circled point shown here is the maximum amount of cakes that can be produced, given the bakery's current resources. In order to maximize the constrained function, we need to use something called the Lagrange multiplier. The Lagrange multiplier is a proportionality constant which is shown by the Greek symbol lambda. This is then solved by finding the gradient vector of P of x, y, and setting it equal to lambda times the gradient vector of g of x, y, or the constraint function. First, we calculate the components of the gradient vectors of both P of x and g of x. We then solve for x and y respectively. You may notice that x and y are functions and that there is still a lambda in the solutions. Don't worry, that will get taken care of in the next slide. Once we substitute x and y into the constraint function, we then have a new constraint function that is in terms of lambda. After plugging in both x and y respectively into the constraint function and solving, we find that lambda is equal to 20. After substituting 20 for lambda into the x and y equations, we find that x is equal to 370 and y is equal to 980. After plugging in 370 and 980 into the original profit function, the profit of Janique's Bakery is $128,080. Note the differences of x and y and of the total profit. After plugging in the additional cakes that can be made into the constraint function, we find that we need 4.5 additional pounds of chocolate to make these cakes. At $25 per pound, for these 4.5 pounds of chocolate will cost Janique and her bakery $112.50. Is it financially wise for Janique to purchase more European chocolate in order to make these extra cakes? When we add the 5 additional chocolate cakes and the 20 additional extra special chocolate cakes into the amount, you would think that the profit would increase. However, this is not the case. The profit actually decreases from $128,125 to $128,012.50. This occurs because of the cost to buy the additional chocolate. The loss of the bakery's profits is $67.50 when compared to the amount that they could actually produce while being constrained. That amount being $128,080. In conclusion, it would not be financially wise for Janique's Bakery to purchase the additional chocolate needed to produce the extra cakes. Janique's Bakery can still produce 370 regular chocolate cakes and 980 extra special chocolate cakes for a profit of $128,080. Thank you for listening and coming along this journey of baking with calculus.